Are you ready to make that a thing of the past? It's time to step up our energy game. Our essential services, our banking, our healthcare should not rely on a fragile system. Our industry, our economy should not be limited by an out-of-date system. Isn't it odd that over the past few decades, technology has advanced so quickly? I'm talking about the internet, smartphones. But the very system that underpins all of this, the electricity system, hasn't changed in over 100 years. It's time to decide what we want our energy future to look like. Here's how I see it. We need an energy future that's resilient. We need reliable and secure power to our homes and businesses. We need an energy future that's productive. We need to minimize waste and minimize cost. We need an energy future that's dynamic. The system needs to handle whatever we throw at it and bounce back, whether that be electric vehicles, renewable generation, or smart cities. This future starts tonight with a system called the Faraday Grid. Let me take you through it. The Faraday Grid is a game-changing way for the electricity system to work. Through planned device upgrades, we're able to transform the 100-year-old system of poles and wires into a multi-highway intelligent platform at no additional cost. It's the transformation from fragile to robust, from wasteful to efficient, from passive to active. It's like the jump from the old rotary dial telephone to the smart device in your pocket tonight. But of course I'm going to say that. I wrote the patents. So instead of just talking big, tonight I wanted to show you. I wanted to show you what our technology is capable of doing and all of the value that it can add. The Faraday Grid arises from a network of our patented power flow control devices called the Faraday Exchangers. We have an exchanger here in front of you tonight. These exchangers are designed to be ready to connect into key points in the electricity system. Think of it like a router for the internet of electricity. Just like a router was able to be put into the old telephone system, transforming those copper wires into something much more valuable, the internet, the Faraday Exchanger is able to be dropped into the existing electricity system and turn it into the Faraday Grid. This device here tonight is a 3-phase device. That means we can have 3 waves of power going through it at a time. It's connected to a live test kit and have engineers backstage that are going to be able to simulate and adjust the power flow going into this device live tonight to recreate issues that we see in the electricity grid every minute of every day. That video was then backstage taken earlier today during our dress rehearsal, and everything is, I'm sure, is going to go exactly as planned, given that it's live. Now, quick disclaimer, I am an engineer as well, and as some of you will know, I am prone to talk like one at some times. So, this exchanger is both elegantly simple, but it's wickedly complex. I promise to be on my best behavior and spare you all the geeky details, but there are 4 things that I want to take us through tonight. These 4 are power level, quality, efficiency, and balance. These 4 things are crucial to our electricity grid. They determine everything from how much we pay for electricity to the reliability of the entire system. The Faraday Exchanger can control all 4 of these at the same time. But what's really interesting is when we put multiple exchangers within a system, they collaborate and they form a Faraday grid. But let's get back to that a bit later on. Let's get into the live testing. So tonight we're going to take a tour of this virtual city. We're going to be able to zoom into different locations and look at how the Faraday Exchanger is able to resolve problems. Whilst the city is virtual, the information we're going to see on the screen about the performance of the device is very much live. The first thing we're going to look at is power level. For this one, we're going to look at a house. This could be your home. Power level is so important. We have to maintain the balance in the system at all times. As most of you will know, when you plug a device in at home, you get 110 volts. That's the power level that we need to maintain. So on the screen here, we can see the power level in the grid itself is on the left, and then the power level flowing into our home is on the right. If the power level in the grid gets too high, that gets passed through to our house, and we risk damaging our equipment. We could literally blow something up. If it gets too low, our devices aren't going to work properly. This is when we get blackouts. It's really crucial that we maintain this balance at all times for the electricity grid to work. So when we turn on the Faraday Exchanger, what we'll want to see is that even if we have the power level fluctuating in the grid, we're able to maintain that nice steady 110 volts into our homes. Okay, team, let's turn on the Faraday Exchanger. There you have it. You can see now that even though we still have the power level in the grid fluctuating, the Faraday Exchanger is able to maintain that nice 110 volts for our devices at home. That means they're going to work more efficiently and much better. So let's move on to our second test tonight. This one's power quality. This time we're going to look at a hospital. So when we're in our homes, our devices, our TVs, our laptops, they're designed to deal with a lower level quality power. In a hospital, we have really sensitive medical equipment. This needs the highest quality power, otherwise it won't work properly. In this case, it can literally be life or death. Power through our grid is a wave. We can see here this power wave through the grid, again on the left-hand side, and then it's passed through to the hospital, and that's shown on the right-hand side. For high quality power, we want this wave to be nice and clean and smooth. If we were to introduce some noise into this wave, or as engineers call it, harmonics, you see that it's going to impact the ability of the equipment in the hospital to operate correctly. Obviously, this isn't ideal, so when we turn on the Faraday Exchanger, we'll want to see that despite any noise in the grid itself, we're able to provide the hospital with that high quality power it so desperately needs. Okay guys, let's turn on the Faraday Exchanger control. Again, now we can see that once the Faraday Exchanger is turned on and controlling this, we're able to take this noise out of the system. This means that our hospital has this high quality power and its medical equipment's going to work. As an added bonus, it also means the hospital doesn't need to invest in its own expensive equipment to do this. The Faraday Grid's providing it for it. So, 2 from 2. We've got the right power level and we've got good quality power. The next thing we want to look at is efficiency. In this case, we're going to look at a factory within the grid. Now, factory uses a lot of energy. So that means it can have a big impact on how the grid's operating. In this case, the factory is not only using energy, but it's also affecting the efficiency of the electricity grid it's connected to. So we're going to do things a little bit differently this time. Because of the way our devices use electrical power, the factory's efficiency on the right will impact the grid efficiency on the left. So if at the moment we can see that the grid efficiency, the factory efficiency on the right is up at 100%. But if this drops, we'll see that this inefficiency is passed through to the grid. What we'll want to see when we turn the Faraday Exchanger on is even if the factory is inefficient, we're able to shield the grid from this inefficiency. So, guys, can we turn on the Faraday Exchanger control? So now we can see on the right, the factory is still at a lower efficiency, but the Faraday grid has been able to bring the grid efficiency much higher, back up to almost 100%. It's able to do this dynamically as well. So if the factory efficiency was to continue to change, the Faraday grid would be able to directly compensate and bring it straight back up. So, 3 from 3. Let's move on to our fourth one. This time we're going to look at balance. So in our first 3 live tests, we were able to show that we were able to control our power level, our quality. You may have noticed that here we've got a street and we have 3 houses on the street. Now, when we showed a house at the start, we still had 3 power levels, but a house is actually only going to use 1. We still decided to show 3 for a single house because it's more difficult to do and we wanted to show off. But in this case, we have our 3 power levels on the grid on the left and 3 power levels on the right, 1 going into each house. So we transport energy through the electricity grid in groups of 3 because it's more efficient for us to do it that way. And to be its most efficient, we want all 3 to be at the same level at all times. But what would that mean in reality? It would mean that these 3 houses would have to use the same amount of electricity at all times. That's clearly ridiculous. Can you imagine your neighbour calling you up and saying, I'm going to go on a date tonight, can you please make sure you don't watch TV and turn your lights off, we've got to keep the grid balanced. That's obviously not going to happen. We can see here that one of our houses has changed the amount of energy it's using and is drawing less. So our top line has come down. This means in the grid, our 3 power levels are no longer balanced. What we will want to see is that when the exchanger turns on to control this, it brings the 3 grid power levels in balance. So for the final time, guys, can we turn the exchanger control on? And there we go. With the exchanger on, even though the houses are using different amounts of power, in the grid itself, we still have this nice balanced power flow. This means the grid's going to be more efficient. So well done to the team. We got 4 from 4, a perfect score. You can all relax backstage now. We've been able to show that we can do our power level, we can do our efficiency, we can do our quality, and we can balance. As I said at the start, the Faraday Exchanger is a remarkable piece of technology, but what's amazing is when we put multiple devices into the electricity grid and they collaborate, they coordinate to form a Faraday grid. The value that they deliver as a system is far greater than any one device can do on its own. To demonstrate this, let's look at a city. Now, we weren't able to bring an entire city in here to demonstrate live tonight, but within this virtual city, we have a central business district. It's using a lot of power. It's very congested. But what happens when an area of this city needs more power? The way that we balance the grid, the way that we provide the stability in order to do this is from external generation. This is both really expensive and actually quite slow. The Faraday grid is able to provide this stability from the grid itself without relying on this external generation. And the way that we're able to do that is like how the internet works. The technical term is autonomous, decentralized control, which sounds really fancy, but what it basically means is there is no master controller. There is no supercomputer using the internet to monitor all of our energy usage and trying to balance the most complex thing we have. Each Faraday Exchanger in the grid looks after its local area, balancing, providing the stability there. But each exchanger coordinates with the other ones and is able to provide total system stability. This is much more robust. It means there's no single point of failure within the grid. But it also means that we have better security. We're not connecting our entire electricity system to the internet and all of the cybersecurity threats that come along with that. So now we have a Faraday grid. We have a more resilient electricity grid. But what about productivity? The cost of energy is so complex. But did you know that half of the cost of energy has nothing to do with the cost of generation? It's just the cost of getting the energy to you. In the areas like New York, which have high energy usage, this can be up to 80% of your electricity bill. A big chunk of this cost comes from balancing the system. But as we've just seen, the Faraday grid can provide that stability from the grid itself. This means that we can do it in the cheapest possible way. Faraday grid also handles renewables better because of this stability it provides. That's great for the environment, but it also means because of this stability, we can put more renewables into the electricity grid. The cost of renewable generation is dropping, but because of the way we operate, we actually get more out of our existing and renewable energy generation. We're basically getting power for free from them. And whilst we're minimising this waste, we're also making the grid more efficient. This means that we can get more useful active power through the system without needing more expensive poles and wires. As we continue to grow our energy use, we'll need less upgrades. The US currently spends over $50 billion a year on this, so there's some significant savings to be had. Because Faraday Grid is able to control the power flows and balance the grid, it's inherently flexible. What this means is the grid's weaknesses suddenly become its strengths. What we get is a platform that embraces change because it has this stability from within. It embraces new technology, new innovation. Electric vehicles is a great example of this. The current system cannot support the amount of electric vehicles we want to have in the future. I was talking with a utility recently who told me they believe their grid can only handle 4 electric vehicles per street. Just 4. Can you imagine having to flip a coin with your neighbour to see who gets to keep their car? Obviously, we have some serious work to do on the electricity grid. We're going to need new types of generation, microgrids, smart city technologies, batteries, artificial intelligence. We need to allow the best minds in this country, and indeed the world, to keep improving on this system that's the very underpinning of our way of life. Faraday Grid enables this because it's designed to be dynamic, flexible, scalable, and that's what our future energy system needs to look like. Because what we have now is not fit for the future. We know something needs to change, but we have a choice. We can either see this as the hardest challenge of a generation, or we can see it as the opportunity of a lifetime. When we designed Faraday Grid, we didn't look at the existing system and try to make it a little bit better. We looked at what the future of energy would need to look like and worked backwards from that. We wanted to create a platform, an ecosystem for innovation to allow us to deliver on that future. How can we know what that future is going to look like? Honestly, no one can, but there's a couple of things that we can be certain of. We know that we'll want energy delivered to us reliably and securely. We know that we want it to be as cheap as possible. And we know that we'll want it to dynamically handle all of these changes that are coming. The Faraday Grid does all of these things. You know, there was an important anniversary a couple of weeks ago. Does anybody remember? The internet. The internet turned 30 years old a few weeks ago, younger than a few of us in the room tonight. Do you remember what it was like before the internet? I'm talking about Google Maps, Uber, Amazon. The way these things have changed our lives for the better is truly immeasurable. Faraday Grid is like the internet. The sum of the whole is much greater than the sum of its parts. The technology is truly impressive, but the real value lies in all the possibilities that it enables. Without the Faraday Grid, they don't have the chance to make that change. So the choice is up to us. The opportunity's here, the technology's here. All we have to do is to decide to act and make it a reality now. So in 30 years' time, we all look back on this night and are saying, do you remember what it was like before the Faraday Grid? Thank you.